Welcome to another Fibre Laser Learning Lab. Today we're going to carry on with some stuff that we investigated a few sessions ago. The strange effects of 1 micron light on various materials. You may remember that I experimented with some glass. We'd already found out that, for example, that clear materials that we can see through, it appears that 1 micron light can see through. Here I've got a piece of clear acrylic. It would appear that 1 micron light goes right through that and has no effect on the acrylic at all, in the same way that it has no effect on glass or on water. Whereas when we fire the 1 micron light at clear polycarbonate, it definitely has an effect. So it must all be down to the atomic and the molecular structure of the material itself. When you fire the laser at glass and it passes right through the glass, if you've got a piece of metal underneath the glass, you vaporize the metal and you deposit the vapor onto the back of the glass. Fascinating process. So one of the strange thoughts that I had was that, can I do it on acrylic? Well, the answer really is no, because acrylic melts at 160 degrees C and it boils and vaporizes at 200 degrees C. Whereas vaporizing this copper is up in the over 1000 degrees C. So I'm going to do some serious damage to the back surface of this acrylic. Hang about. Isn't that what I want? If I can fire the light through the acrylic, bounce it off the surface of the copper or stainless steel or aluminium or any other metal that I choose to use, does that mean to say that I can actually engrave on the back of this? I don't want to vapor deposit any metal onto it. I just want to create enough heat reflected off of the metal to damage the surface of the material. It should be possible. So let's go and experiment. Bear in mind some of the other lessons that we've learned about this machine, and we've been warned that we shouldn't actually try and work below the focal point, or we shouldn't try and reflect metals back up into the lens. So I've got this work pushed across to the side so that it's not reflecting directly back into the lens, but if it's going to do anything, it's going to reflect off somewhere else into space. So the first thing I'm going to do is set the part height to 1.5 millimeters, which is the thickness of the copper. So we're actually going to reflect off of the surface of the copper, because that's the plan. And the answer is not a lot. We've managed to mark the copper, but we've not generated enough heat for long enough to damage the acrylic. Well, again, it's done a great job of marking the... Oh, look, we've got something on our acrylic. Not a lot, because look, I can wipe it off. So it must be basically almost smoke. But let's go down a little bit lower to 500 with our speed. Put more pulses in per unit of time. Now that's something rather interesting happening there. Hopefully you did as well. You noticed some speckles and some sparks as it was engraving. Now we've got a really strange effect starting to happen now. We have not really, well, we've marked the back, but I don't know whether you can catch it in the light there just right. Something is happening inside the material, because it isn't just a mark on the back. We've got, when I catch it in the light just right, I can see some little sparkles in there. We'll take the speed down to 250 now. Now look at all that. Look at all that's happening inside there. Now what's happening there? Something weird has taken place. Look, I've got a whole load of bubbles or something taking place inside the material. Normally we wouldn't be able to mark this at all. Let's try a different sort of material underneath here as a back reflector. Let's try some aluminium. Won't change the settings. I've still got the focus basically down on this surface here. Whoa. So we're busy exploding the material. We must be producing bubbles inside there. We must be vaporizing the material somehow inside the acrylic, and it's expanding, and as you heard it pop as it exploded. I certainly don't appear to be succeeding at burning the surface of this and heating the surface of the acrylic. I've got no idea what I am doing, but hey, that's not unusual for me. Now, because I've got an air gap under there now, I'm going to produce the surface marking, and I'm going to get quite high temperature ionized gas which is coming off the surface, producing that's what that white flame is, you know, it's ionized gas. If I put the material straight down onto the surface, I'm preventing any oxygen from getting to the surface, and so I'm basically preventing ionization taking place. Well, we get a lot more noise. We also get less explosive burning. And what we're picking up now is all these bubbles from underneath, which is this surface here. Now that gives the impression that we're doing something with a reflection. Now, let's try the same thing with copper. What copper does, as opposed to aluminium. We're getting some sort of effect which is coming up from a reflected image. I think the first thing we'll do is see if we can control the damage that we're getting in there. Can we stop it being quite as violent as this? Because look, some of it is explosive and burning out. So let's put the speed back up to 500. So we're putting less power in. So let's go back from 500 back to, say, 300. Still taking place from the underneath here, and we've got a little bit of damage on the underneath surface. But as you can see, the burning, the bubbles are taking place low down. Can I change the position of those bubbles by changing the focus? At the moment the focus is set onto this surface here, and it's reflecting back up into this material. What happens if I put the focus on the top surface, I wonder? Let's come right up to the top. So instead of 1.5 for my part depth, it'll be 1.5 plus 1.5, which is 3, plus 9.5, which is 12.5. So we'll keep the settings exactly the same, but we'll change the focus, 12.5, to see if this is somehow related to focal depth or reflections, or I've got no idea what it is at the moment, because we shouldn't be achieving anything inside that material. When we look at it from the side there, look, it's now passing fairly uniformly all through the material. We increase the power by putting the speed down. Let's go back to 200. See, we're getting burning at the surface now. We're definitely getting a lot of bubbles, and they're not going completely all the way through. They're from the surface down to maybe 6 or 7 millimeters into the material. That's where the density of it is. I don't know whether you can see that. Look, can you see this strange pattern here? Look, that's a shear plane. That's an exposure plane within the material. It's actually opened up a void. So we're definitely producing gas inside the material. At the moment I've got a pulse width of 250 nanoseconds, which is quite a lot of power per pulse. Let's back that off to something like maybe 100. We've still got, you saw that shear plane open up just there. At the moment the scan lines are 0.05. We could increase the power by 5 times if I decrease the interval to 0.01. Aha! We've got nothing coming out of the surface at the top now. We've got some very nice bubbles in there. In fact, it's most of the energy, most of the bubbles are in the center. So if I take a nice clean version so there's no confusion, and we'll repeat that test. We've got very little blowing out the top this time. Most of those sparks are down the inside, but most of the energy is in the center. At the moment I've got the focus set to 12.5. Let me lift the focus, let me lift the material thickness, which will effectively pull the focal point up above the material. I'm going to take it up to 15 millimeters. Well, it certainly has an effect. I think you can clearly see there, look, it's brought it right up to the top surface. So whatever is happening, it's got something to do with the focus. Question is that the focus combined with a reflection? How much is the reflection playing on this? How can we test that? Very simple. We have a piece of paper. Now we know that this stuff doesn't pass through paper, so this will begin to tell us, hopefully, what's going on. And the answer is it's got nothing to do with the reflection by the look of it, because we've got no change in the result. I mean, we shouldn't be able to mark this material at all because the light is passing through it. So we have to ask the question, how is it possible to mark the material? I'm going to change that part height from 15, which is about 3 millimeters above the material at the moment. I'm going to go right up to 20 millimeters and see what happens. Here we go. I can see a few little flickers right down on the bottom surface now. Whatever it is all down to focus. Let's go the other way and drop it halfway into the material. And we're now getting an effect of some sort. And whereas my thoughts were that it was to do with reflections and interference between beams, the fact that there is no reflection there tells me it's all to do with the focus. But how can that be? What is happening? So after a few more experiments, I've got what I think is a pretty good set of parameters. It still doesn't explain what we've got here, but I'm going to run this and then we're going to probably have a look at it under the microscope to see if we can first of all see what these so-called bubbles are. They must be bubbles you've got to be evaporating little teeny weeny chunks of material and turning them into gas. The longer pulse is actually not as good as the shorter pulse. 20 nanoseconds, 115. Yeah, we've got a lot more sparkle in there now. This one's a shorter pulse time, and it's beginning to look quite a lot better, and it's more uniform throughout. Let's try 13 nanoseconds. It's pretty uniform throughout. Look, it's gone all the way through the material there, pretty. But it just doesn't look. I mean, it's 3D, which makes it interesting. I would like to see it so it's obvious on the surface, like one of the others that we produced. And we did that by pulling the focus up a little bit. So at the moment it's set to 8mm, which is 3mm to there, and 5mm away from 9.5, which means it's 4.5 into the material. Right, well, let's give this a try, shall we? This is 1500mm a second, 75 kilohertz, 45 nanosecond pulse, and we've got a 0.01 interval between the line scans. So we're 4.5 into the material. Now, as you can see, that looks pretty uniform. Although we've got some density at the top, we've got quite a lot happening down below. Let's see what sort of surface. Well, you see, that's getting better. That's getting, because we've got it closer to the surface, a little bit more visible on the surface itself. When I put some LED lights behind it, look. It's looking pretty good. Okay, so here we are in the office with my low-powered USB microscope, because my big microscope is just too powerful to see what's going on. Now, it's interesting to note that what I've got here is a piece of pink paper in the background with some pink strands in it, as you can see. And you can see that they are nicely in focus, the background. So I'm focused through the material onto the background. But look what happens when I draw the material away. The background has gone out of focus. So the material is already having an effect on the light and the way it's focused. So there's some strange effects going on inside this material, even with visible light. Now, when we start looking at the bubbles that I've produced, what we're looking at now are the bubbles that are right down on the bottom surface. Let's just move across a little bit and see. Ah, there we go. Now, that's not untypical of what I'm finding. If we take a look here, you'll see that we've got like a little white blob. That's a bubble. But what it's done, it's exploded inside the material, and look, it's produced this like a halo. It's almost like when I look inside this material, look, you've got all these different oval shapes. Look, there's one there that looks like Saturn, look, you know, with its rings. And all of these look like little mini universes. They're all laid at different angles, and they're all fracture planes. You've got a little teeny weeny spot of gas that's appeared in the middle, and it's then exploded out, pushed out, and managed to shear a plane around it. And that's what these are all looking like. So the acrylic melts, at 160 degrees C. It then turns into vapour, like steam, at 200 degrees C. But unlike steam, it is a volatile chemical. It's got hydrocarbons in it. Whatever heating is taking place in there has also heated up the vapour and turned that vapour into like a sooty material. It's almost oxidised it and turned it into a sooty material. And there's lots of these little teeny weeny black spots around in here. So we've got like a double chemical reaction taking place. Some of them are low temperature and they just produce a little teeny weeny white bubble with a fracture plane, and some of them are these very dark spots. Where are these little spikes of energy coming from? They're spikes of energy which are doing damage to a material that would normally allow the light to pass through. So we must be experiencing some sort of interference pattern between the light waves, which is causing some increase in energy, intensity. And this shows us what happens to light as it passes through a transparent material like glass or acrylic. So the light approaching the transparent material is at a fixed frequency, and it hits the material and slows down. Now, the frequency does not change because the frequency is the colour of the light. You can say, well, yeah, I can see the frequency has slowed down. Well, no, what's happened is the wavelength has shortened. If you count the number of pulses passing by a single point, you'll find that there's just as many peaks passing the point on the left and the right as there are passing any point within the glass. We've got more peaks passing a point in the same period of time. So within the material, we've got a lot more light waves. But because the colour of light is defined by its frequency and not by its wavelength, then the light has remained unchanged in terms of its colour. I'm trying to make sense of why and how you can get splashes of power inside the material. You do get a crowding effect of waves inside the material. Now, the other thing that we have to take into account is the fact that the beam is not parallel. We're busy focusing the beam down. So by very, very definition, the waves that are running down this beam are not running parallel to each other. And as I've mentioned maybe on a couple of occasions before, I'm a little bit puzzled because if the waves are travelling different distances, then they are basically travelling at the same speed, because as we've seen from the previous diagram, the waves go in at one speed, slow down, and then they come out at the same speed. So they're both travelling, these waves are both travelling at the same speed, but technically they're travelling different distances because they're on different legs of the triangle. So they therefore must get out of phase. The problem with things getting out of phase is you get something called superposition. The waves, although they're coming from the same light source and they're at the same frequency, they're not running perfectly together. And when you get superposition of waves, according to wave theory, you get interference. Now, let's just have a quick look at another diagram that I've knocked up quickly. And here we can see two waves running towards a focal point. They're gradually getting closer and closer and closer, and they are the same frequency, right? But if they are the same frequency, this wave and this wave, they can exist in the same space without interfering with each other. So in this case, look, we've got this wave running at a very slight angle to the other wave, and when they cross over, they will cross over and carry on as normal. So they start off as two waves and they finish up as two waves. But at the point where they physically occupy the same space, something strange happens. And they either become additive, as in this case, because we've got two waves that are the same frequency and the same amplitude. The amplitudes add. so we get double the amplitude at just a very small section where the waves try to occupy the same space. Now, because these are coming down at a very gentle angle, I mean, I've only drawn one super plus wave there, but it could well be that there are 2 or 3 or 4 which are gradually building to a plus and then back again, and so we don't just get one, we get a pulse of several waves. But those waves, the energy at that point is much more than the single wave energy. Whereas if they get out of phase like this and they stay out of phase, then you never get this plus. We're always getting minuses. Okay, so this is what happens when they're in phase, which is probably a very rare situation, but here's what happens when they're out of phase. Okay, the same applies here. So you get no plus pulses, so it's only on this one special situation where you could get some very high energy pulses. Now, this is the only thing that I can think of that fits the random sparkle that we've got in our material. So we know at this point here we've got relatively low energy density. We're not able to do a lot of damage, and it's only when we start compressing the waves together that we increase the intensity of the light. We're not changing the amplitude of the light, we're just changing the density of the closeness of the waves, effectively putting more energy into one specific point, more intensity. So if we want to detune the intensity at this point here, we've got several ways of doing it. One of them is to change the amplitude of these waves, and we do that with the power. So we can reduce the power, which means we get smaller waves, which means we shall get less big pulses because they won't double up as much. So that's one way that we can decrease the power. The other way that we can decrease the power is to defocus. In other words, we can move a long way above or a long way below the focal point, and then we shall finish up with, if you like, waves like this, where they're quite a long way apart and they're not going to interfere with each other. And even if they interfere with each other, they're so weak at that point because they're not crushed together that they won't actually do any damage. That we cannot get any high spikes of energy. We're going to go back to the machine. If we can find the point at which we get the maximum density of this the maximum density of our bubbles in the center of the material, okay, we should be able to detune with reducing the power to make the bubbles less. So we leave the focus as it is, and we should be able to tune the bubbles out. We should be able to lift the focus up and lift the focus down and bring this point closer and further away from the top or the bottom of the material. It's the only mechanism that I can envisage which will excite the molecules within the material. When light collides, normally it's the surface atoms and molecules that get vibrated to a higher temperature. Well, here we're not vibrating surface molecules to a higher temperature, we're vibrating molecules within the structure to a higher temperature. So something very strange is taking place to cause little pulses of energy within the material itself to vibrate the molecules up to a high enough level where they vaporize, and even within the vapor we might even be burning the vapor and turning it into a carbony type material. It's a fascinating idea. I've looked around a lot and I can find nothing by way of research to explain what's going on. I've got a 1-inch block of acrylic, and I'm going to stand it on edge this time so that we can see the penetration into the material rather than sort of try and guess what's happening through the thickness of the material. You can immediately see that actually it looks as though the densest part of that is probably around about 3 or 4 millimeters down into the material. So perhaps the first thing I should do is raise the height from 25 to 28 millimeters. In other words, I'll lift the focus 3 millimeters out of the material to see whether or not it'll drag the pattern upwards. This one is frequency of 75 with a 45 nanosecond pulse. We're using 100% power and 1500 millimeters a second, and we're now 3 millimeters above the work with the focal point. And it actually looks quite nice on the surface as well, doesn't it? So now I'll go the other way and we'll go 3 millimeters into the material. And yes, as you can see, we've dropped it down into the material. There's no doubt it's focus related. So the one at the bottom was 3 millimeters high, and the one at the top here is 3 millimeters low. So this time we'll have a go at reducing the power. We've got a fixed pulse width of 45, and the last time we did this we had just a little bit of crackle and pop on the surface. So we'll reduce the power now to 80%. It should reduce the density of the bubble, it should reduce the density of the bubbles, and also the risk of it going snap, crackle and pop. Well, that's pretty amazing, isn't it? For just a small change of power, 20%, we've virtually lost it. We'll put the power back up to 100%. Running slower puts more pulses into the job. So let's reduce it from 1500 to 1000. And now we probably will expect to find more bubbles or more shear planes and more crackling and popping. Well, we're running slower and it probably looks as though we've got a greater density without actually causing too much more physical damage. Yeah, I mean, it's down below the surface. So let's leave it at 1000 and raise the part height again. In other words, we'll take it 3 millimeters out above the surface to try and bring the pattern right back onto the surface. Now, although we've taken it up to the surface, we haven't actually caused too much more damage. In fact, there's less density there, which is surprising. I would have thought there'd have been more density there. So we get more bubbles in there by probably then closing up the gap between the lines. So we're on 1000 speed, 100% power, frequency 75, pulse width 45, and line spacing 5 microns. And we got a focus height of 28, 3 millimeters above the surface. Now we're cooking, really cooking. Look at all that stuff going up in the air. That's gas, I presume, which is igniting. They're vapours that are igniting. We've just burst out the top there with melted acrylic, look. So now we're at 8 microns line spacing. Ooh. That's not bad, but we did get a bit of popping and crackling, didn't we? I tell you what I'm going to do. I'm going to push the speed from I'm going to leave it where it is, 0.08, where we got our crackling and popping, and we're going to push the speed up instead to 2000 from 1000. So we've doubled the speed and we've really lost most of our bubbles. So here we are with 30 millimeters above, which is 5 millimeters above the surface. We've still got our 45 nanosecond pulse, 800 millimeters a second and 100% power, and a 0.01 line spacing. Well, I don't think there's any doubt about it now. It's something to do with the focal point. But we've got nothing that I would consider on the top there to be text. It's not readable text. It's not sufficiently dense enough. So there's our initial settings with the focus on the surface, and it clearly shows that there's something happening, 3-4 millimeters below the focal point. That's where all this problem is occurring. It's not occurring before the focal point. And we can prove that, and we'll see what happens when we push it down to, say, 5 millimeters into the material. So we'll go down to 20 millimeters. Okay, with those self-same settings now, we'll turn the job over and we'll see what happens at 20 millimeters. Do we lose the pattern because the energy is being absorbed before it gets to the focal point, or is it going to drop the pattern down by 5 millimeters? Theoretically, this material is transparent to 1 micron light. So dropping the beam down by 5 millimeters should have no effect on the beam itself, and our pattern should drop down by 5 millimeters. Well, it certainly looks as though it might have done. We've got some other slightly higher density patterns starting to happen just across the top there. So let's drop it another 5 millimeters and see what happens. So the focus is now 10 millimeters down into the material. You can see where our bubbles is, our bubbles. Our bubbles is now about there. That's pretty interesting, isn't it? It's dropped it right the way down. Look, we've lost it. We're no longer at the surface. Roughly where my thumbnail is where the focal point is. So that's damage above the focal point. So if I lift that up by about 3 millimeters, it should bring that bubbles back onto the surface. And there we are, we've got our bubbles virtually back onto the surface. But that line is where the focal point is. And I think you can see it looks as though we've got another pattern building below the focal point as well as the one above the focal point. So when I raise the focal point up to the top on this one, I've got my bubbles here, which are obviously this pattern here. So whatever's happening is above and below the focal point. It's not at the focal point. it hasn't really proved the point about the wave theory idea of superposition and the addition or the extra power. For a material that shouldn't mark, we've been able to mark it. We've been able to create a problem inside there, and we've got control of it. Now, whether this is interference caused by colliding light waves adding together to increase the power at specific spots, and of course it will be totally random because every pulse will be different, which is why we've got a range there. In fact, we've got two ranges, one above and one below the focal point. Now we push one of these down to 15 and we found our bubble was sitting just across there. So now the focus is only 5mm above this base. How weird. How weird is that? That's not building up from the top downwards. All of a sudden it's building up from the bottom upwards. How's that? Is that internal reflection off the bottom face of that material? I'll tell you what I'm going to do. I'm going to try 25mm. I'm going to focus directly on this piece of paper. And, much as we expected originally, I don't think we've got anything there, have we? Doesn't look like we've got anything there. Does that mean to say the energy has gone right the way through that block with no obstruction? We have a piece of stainless steel there which will mark. So if the light energy is passing right through that block, it will mark that stainless steel. So we'll just change the part height to 1mm. Oh, we've got a few little sparkles in here, look. And we've got a few little sparkles at the bottom. And we've got some energy that went through. But let's just see what the energy is by running the same test again without the acrylic in the way. Well, that is interesting, isn't it? That means that acrylic is not that transparent. Put enough of it in the way and it will absorb the energy. So therefore I think we're beginning to prove, yes, that at certain focal points within the acrylic we are creating little bundles or bursts of energy that are able to damage internally the acrylic. Now if you make the acrylic thin enough, it will pass right through, but make it thick enough and it will absorb the energy. Now the other thing that shows clearly is that we've been able to produce a nice gold finish on stainless steel. Now that's not the first time we've done that, is it? Looking through the clear face of this perspex, it's much easier to see this little universe of spiral galaxies almost. Look, every one of these has got a little teeny weeny bubble in the centre, a little gas bubble, which has caused these to produce all these little shear planes that go in lots of different directions. So there is no uniformity about these, and they're not really bubbles. The light seems to be catching like the rings around Saturn. It's the shear planes that are picking up the light and making it look like bubbles. So we started off trying to mark the acrylic by a burning reaction process. We failed miserably at that, but succeeded at something else that we didn't really expect to find, which is this bubble effect within the acrylic. So I think the proposal that I made earlier about light wave interference patterns is not disproven, but it looks credible. Is this of any use? Well, I think it could be of use if you're making trophies and things. You know, it could be quite an interesting trophy, and especially if you can edge light it. It's certainly no good for photo replication work because the dots are so randomly scattered, you've got no control of them. But for text work, you could make some quite nice text trophies maybe. For instance, I could imagine a very nice clock made with this because the letters would stand out well, especially if you edge light it. I'm only here exploring what's possible. I'm not attempting to utilise this in any way at all. It's just an interesting phenomenon that we've discovered about acrylic. I think we'll stop there and say thank you very much for your time and your patience, and I'll catch up with you in the next session.